Okay. Can you hear Jonathan? Okay, thanks. All right, so we start. Oh, sorry, I'm going to around. Well, thanks. Okay, so then we start a bit earlier, then we can all go for lunch a bit sooner. So today we have a special guest, Alexandre, who is 13, and she's watching. They do this thing into schools where you follow an adult, I guess, around during the day to see what their work is like. So she's doing this. So as a consequence, today's lecture will have less calculations than usual. It will be a bit more informal. Is that a good thing? Okay. Okay, so we'll talk about the double slit experiment, and we already hinted at it, and now we're going to see it in more detail. In particular, talk about intuition, some of the key insights and conclusions, but I will not do the full calculation of the evolution of the wave function. We will start, yeah, Kevin, sorry, we started a bit earlier. So we will start an approximate, a simplified setting, then we'll do the calculation next week. Yep. So what's the setting of the double slit experiment? As probably everyone heard already, is that you have some kind of wall with just two small slits. So let's say there's some distance between them. And then at some point later, you have a screen. And you shoot some particle at it. So you send some particle from here. Could be an electron, or it could be photons. Or you can even think about what happens if you shoot water through here. Yep. And the thing is that, well, maybe experimentally I can try to draw the example. So they shoot an electron. You know, sometimes the electron will hit here, the wall, and then you don't see anything. But in the cases, post-selecting in the cases where the electron passes through, you know, it will hit somewhere here. And then maybe I'll do in a different color. Oh. Okay. Somewhere there. And then you send another one, and it goes maybe there, and another one, and another one, and another one. And after a while, you get this kind of pattern where there's some areas where you see lots of electrons hitting. And this is, it doesn't depend if you send them faster or slower all at once. There's some areas that will be a bit darker because all the electrons hit there, and somewhere nothing happened. So from here, you can kind of reconstruct that your, you know, the probability of hitting a certain area, which is the square of the wave function, would be something like So it's kind of modulated, it has a higher peak in the center. So this is all you can do just experimentally, right? This is just what we observe. Then the other option is what you do. You do the same experiment, but now you measure from which side the electron goes. How do you do this? Well, for example, you could have a little particle here, some spin S, that reacts to, like, if it fills the wave function here, then it will go to 1 if it goes through the right, or stays in 0 if it goes to the left, using one of these interaction schemes that we saw. I will explain this in more detail later. Okay? But what matters is that you have some register, some of where the particle went through. And in this case, when you do this, well, what you get is, not surprisingly, you send the first electron, and you detect that it came through here, and it ends up somewhere here. And the second one maybe also came through there, ends up somewhere there. And the third one detects that it goes through there, ends up somewhere there. And then you build up something more like this. And here, if you do the same plot, the probability distribution is going to be one big peak here and one peak there. Like this, maybe there's some kind of overlap in this area. Okay. So this is the square of the wave function at that position. In this case, people say, oh, it behaves like a wave, because if I send a wave of water, you can think of it as like you have the kind of the crest of the wave, ends of the wave, and they interfere with each other. And then you see this kind of interference pattern. And here they say, well, it behaves more like a particle, because I can think of, I'm really shooting an electron through here and it really end up somewhere there. Or the electron really comes through there and end up somewhere there, right? And this is like your wave particle duality of, both photons and electrons. You can also do it with atoms. It's a bit harder, but you can do it with everything, right? And this is what all popular science things about physics say, oh, it's a wave, it's a particle, I have strong opinions about this, namely that, these categories, these are things that we build up based on our intuition from classical physics, right? Like that some things are particles and some things are waves, and nature doesn't care, like how you decide to split out your vision of the world. Like nature is deeper and more interesting than being just a particle or a wave. And there's no reason why it should fall into one of these categories. Yes, a bit like gender. Good. So what is happening in both cases? So this is what we're going to look at it now, right? So in this case, when you have here the total wave function, we'll do the proper result later, but it's kind of a mix of the wave of a wave function that goes to the left and one that goes to the right, right? So we have psi is going to be some alpha, a wave function that goes to the left, plus beta, some wave function that goes to the right. And as we already did at the end of the last lecture, when you then do the probability of being at some position x, which is this jack, x jack, or you can do the projectors if you have some wider projector, if you have some non-zero precision. So in this case, we saw that we get L of x, a contribution that is just from the wave function on the left, plus a contribution that is just from the wave function on the right, plus these cross terms, which we will look at in a second in more detail, how they look like. Whereas in this case, what we have, so these are the important cross terms that will cause this interference pattern, which we'll talk about in a moment. And on the right, when you have this observation, what happens is that the particle case is that there was, as it goes through the slit, so let's call this at times equals 0. Maybe you started with this. At times 0, but then you coupled it to some measurement system, I call it here M for measurement. And this I call maybe P for our particle. We couple this through interaction, which is the same as we did in previous lectures. So this went to the state psi L on the particle, 0 on the measurement device, plus beta psi right on the particle, 1 in the measurement device, right? So then when you do at some later time t, if you evolve the particle system with t, then you just have a t here, a t there. But then when we compute the probabilities, they are the same as in the Stern-Gerlach experiment. So then the probability of getting x, then it becomes just of x at time t. You can put here time t, but which this is just the probability of getting x for the left particle, and this is the probability of getting x for the particle on the right. Okay. And you remember this calculation, why it was that the cross terms disappeared is that then when we do the inner product, you have the inner products between the 0 and 1s, which cancel out when they're different, right? You all remember this. Okay. So now what is left to do is to study exactly what this interference is, right? What is happening there in those terms in red. So far, you're with me. So let's just think about how we get interference in the first place. So let me just tell you what the intuition is. Well, the intuition is that you have some wave that is coming in. And it has this oscillation inside, like the E2ikx, for example, right? And then it hits here, so only this bit will survive, and that bit will survive. And you'd have to be very, very lucky for these two things to be like precisely aligned, such that it starts at 0 here and it starts at 0 here, right? Because it's just like you're taking this wave function and you're cutting it there and there. So there will be approximate versions of this. There'll be approximate copies up to this shift in position and some initial phase. We'll see what this is exactly. Yep. So let me just give some names to things here. We call this maybe x0. This little delta is like the size of the slit is 2 delta. And we call the distance between the two L. So let's suppose that before the slit, so at this point here, we have some wave function. I'll call it psi prime because it will change later, which was, and think for now just in one dimension, let's forget about y, ekx. And then it had some kind of envelope, right? Could be a Gaussian, which I didn't draw here, but it could have big envelope. Okay. So this means that a whole state is the integral from -infinity to infinity of this thing. And I can break this integral into 2 parts, for example, -infinity to 0. I don't know, let's say 0. 0 there. dx ikx plus the integral I didn't do anything unusual, right? So normally we just have the integral from minus infinity to plus infinity. Think of it like a sum, and I just break it in two parts. Now, after the slit, and this is not a unitary evolution, but if you wanted to look at the full unitary, you need to see, oh, what happens when we hit here, then, you know, maybe this electron is transformed into a photon or just some thermal fluctuations, whatnot. We don't think about it. We just think about what's kind of the post-selected state, considering that it passes. So we look at so what changes is just the envelope. The thing is still going with the same frequency and momentum. It just changes like how much of it can go through, like the intensity of it, which corresponds to the envelope. So what we have is, so I can do the same thing. So from minus infinity to say 0. And now a new envelope. Let's do this like this. And now this envelope has some particular properties, namely, it is 0 unless you're in this area here. Right, the wave function is going to be 0 everywhere except in this little area, that corresponds to the slits. Is that okay? And it's the same here as there, except shifted by L. Which means that I can replace this integral. So this integral is like an integral over 0, 0, 0, and then over something, and then 0, 0, 0, and then something, right? So I can replace the integral over the whole space by the integral just in the non-zero part. Okay? So that's what I'll do. So let's say it goes here from x0 minus delta to x0 plus delta to I x. New thing. And now we have x0 plus L minus delta, x0 plus L. This is the right slit, x e to I k x. And the envelope is the same as at L. Yeah, that's right. Right, so that this envelope here is the same as there. That's it. Good. So now, I mean, they're looking almost the same, but the problem is that here I have kx, and here I have x minus L, which means I cannot compare directly like this wave function here to this wave function there. So we cheat, obviously. So we multiply, and this is for free. We multiply by e to I k L outside, and then inside e to minus I k L, which just means that here I can do this. X minus L. Right, I didn't do anything. So why did I do that? Well, because now I have something here that is exactly the same as there, just for a different variable. And now you can think, oh, this is almost a state. The only problem is that it's not normalized. And the one on the right is also not normalized. Because, you know, the wave function for everything, the squares must sum up to 1. but we're not there yet. So okay, so I will define now a new wave function. I'll define this psi, the left wave function. No. The left wave function. Well, I just say it's e to I k x. And then this factor here is just so that the whole state will be normalized. If x is in this little interval of the slit, and 0 otherwise. So this is really a wave function that goes 0, 0, 0, chuka, 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 0, 0, 0. Yeah. And now I'll just replace it inside this whole thing. So I have that psi. I mean, what you know is the following. The whole thing needs to be normalized. This is just a phase. This has the same weight as this, right? It's like it's the same thing, right? So if then this square plus this square must be 1, then each of them must be normalized by square root of 2. That's it. I mean, you see that it works out now. The assumption is that this was after the slit. It went from this state to that state plus some trash, which is what happens if the electron hits the wall. And then we renormalize this whole state, right? So it's like post-selecting on the outcomes we want. That's what's happening. So that's why it will be the square root of 2, because now we have that the whole state is 1 over square root of 2 integral. And it could be from x0 minus delta to x0 plus delta, but because this wave function that we define is 0 everywhere else, I can put from minus infinity to plus infinity. The x, L of x. Right, I just replace that directly. Plus 1 over square root of 2 e to ikl dx, and now it's just x minus L. So this is what I call the psi right, and it's normalized now, and this is what I call the psi left. So then the whole thing is just psi left plus e to ikl psi right over square root of 2, which is the kind of situation that we wanted in order to apply this reasoning I had before about that we'll have some interference at the end between these two wave functions. Okay, good. So now, what does this wave function do? What does a phase difference do in terms of interference? We're going to look at a very simple example, which is not this. So make noise. Yeah. Okay, so let's look at just seeing what it does in terms of measurements. And this is a 1D example and simpler than the case that we'll have there. But so suppose that we have this psi equals psi left plus EIKL psi right. But that they don't have this difference in L inside the wave function. We really just have that. So suppose that sorry, psi, in this case, it's psi. They are the same. The only difference is that there's a phase there. Okay, so we look just at the phase, not at the distance between them. So then let's just write what psi L of x is in this case. So suppose it's this I okay, x, right? Then we just expand this thing. So it's cosine of kx plus I sine of. Now let's look at this whole, at what's on the right. So it's e to IKL of x. Well, this is going to be I have x e to IKL plus kx, right? Or in general, it doesn't need to be KL, it could be just any phase gamma here, for example. So then you get the sine of kx. And this changes with x, right? But this thing is just a constant. So if I plot the two, so let's just plot the real part of this. And then you can do the same for the imaginary part. And let's just take the simple case where like we just make this a square function. We can make it a Gaussian later, but that's not what we're trying to look. We're just trying to look at what's the impact of summing these two things. So I'll do this one in red and I'll do this one in yellow. Okay. And I'm just plotting the real part. So the cosine starts in 1, so it goes like this. And the other one is the same thing, just shifted by this KL, right? So instead of starting here, it will start a bit before. And so on, right? So then when we're trying to sum the two for those things, so remember that now Alphas are this, so I just say proportional to square plus these cross terms, right? So even now we're just looking at the real part of this. So we're just looking at the real part of this, guys, and then we could do the same for the imaginary part. And what's important is that, look, there's areas where one of them is still positive, but the other one is already negative. And that's, for example, from here to here, right? In this whole area, we have that the red one, so the one on the left is negative and the other one is still positive. So when you sum them up or when you multiply them, then this is going to be a very small number. So this is areas of what we call destructive interference. Then there's areas of constructive interference, which is when they're both positive. For example, here they're both positive. So if the total wave function is going to be positive, and it's going to have like a big peak here, right? And then you have again an area of destructive interference when they have opposite signs, and so on. Meaning what? Meaning that you can observe in the interference pattern that you get, which is going to be something like this. There'll be some distant delta between the fringes, and this different delta just depends on this phase at time of arrival. Okay. So this depends on K, on L, and of course it depends also on the exact form of the envelope and so on. So all this pattern here will depend also on delta. It depends on the time of evolution, so on. But what this tells us is that from observing just this pattern, we can find out things about this phase. So, and we can find out things about kind of the momentum of the wave function. We can find out things about the distance between the two slits. Given the intensity of it, we can get information about the size of the two slits, like the width of them, and the time of evolution, and so on. Which is super useful. And I'll give you now just examples of applications, right? Because maybe at first people were puzzled by the philosophical implications of whether this meant that it was whether light was a particle or a wave. But soon thereafter, they found out that, you know, despite the philosophy, or beyond that, it can have many, many practical implications. So I'll just give an examples of some. And then what we'll do probably next time is to find the exact expression for that thing in an approximation for this dependency. Questions so far? Yeah. I did, yeah. Yes. Yes, yeah. Yes. Because it's more to give just a qualitative analysis of what's happening, and later on we'll look at the actual quantitative. But just so you know, like this difference of phase comes from the fact that, you know, they hit the slits at different time, at different positions relative to this oscillation, and that this different in phase, this relative phase between the two leads to an interference pattern. This is kind of the takeaway. So applications. So one option is, suppose I'm trying to characterize some light. I'm trying to determine, I don't know, the frequency of the light or the momentum of the light, which is all related to this K. Okay. And I don't know it. Well, if I have a setup with exactly the slits, and I know and L is known, and the little delta is known, and so on, and this distance here is known, then I just send a light. I get the interference pattern here, and I know that this delta depends on my unknown quantity K, and I can do K, right? So people can use this to characterize the momentum, so the Kx of things from photons to electrons to bigger systems. But more, maybe much more used is the case where we know this particle that we're sending in very well. What we don't know is this thing that it is hitting. So for example, I mean, notice now that if I make this L smaller or larger, it will change, it changes the phase, the relative phase, so it changes the interference pattern here. So people can use this to characterize kind of this surface. Of course, it will be more complicated versions of the experiment, but one application is crystallography, which means what? Well, I have some material in which atoms are arranged in some form, in some kind of network, a lattice. And I don't know, for example, this distance L between two atoms in my lattice. This is very used in solid state physics, for example. So what I do is I send electrons, and there will be a diffraction pattern. You know, they kind of see these big atoms almost like walls, and the things between them as slits. So a version of this. So then you end up with some pattern here. And this, I think, is studied a little bit in quantum mechanics too. That then from this pattern here, you can discover the distance between your atoms originally. And it's, again, it's just a more advanced version of the same principle. Or you can do the same if you want to, if you have some surface that you think might be irregular, and for some reason for you, it's very important to know exactly how irregular it is. And this is everywhere in material science. One way to detect like these very distant, very small distances that you cannot observe, I mean, not even with a microscope, is then to send photons here. They'll hit and they'll be diffracted in, reflected in different angles. And then you observe again the interference pattern between them. And from the interference pattern between them, you can infer what the surface was. And now yet another one that was very famous a couple of years ago was to build an interferometer. For example, the ones used to detect gravitational waves. So what's the idea there? You send a wave through a beam splitter. You talked about beam splitters, right? So it splits into two. Let's say this is the left one. This is the right. So it splits into a superposition of left and right. And let's say here. Here they recombine. This is a mirror. And let's say here they recombined. And you look at the interference pattern that they form. Okay, so this beam splitter splits the incoming wave into a superposition of one that goes there and one that comes here. And here's another one, so it's kind of recombined there. And then you just send the final wave, which is the sum, into there. So if they go exactly through the same length, then at the end, they're going to have exactly the same phase. So then there's no interference, right? You end up with this pattern. But if you change this length in one of the arms of the interferometer, right? I make it go through a little bit more distance, then it will end up here with some EIK delta. Okay, if I move this by delta. Okay. something like this. So then it will have a phase difference relative to the wave that went arm. So then you can have this pattern here, and you can use this interference pattern to determine how much you move this mirror. And then what they do is to make these arms very, very, very long and connect one of the mirrors to like a spring so that it can detect. What it does is detect very, very small changes in gravity, which are caused by gravitational waves. You'll have a tutorial about this next week. And then this turns out to be detected here in a way that's macroscopic. So the whole idea of these applications is that through interference patterns, you can really detect very, very tiny changes in position, in length, in a surface that you cannot detect with the naked eye. So this is one of the big applications of this experiment, and a lot of what's done in like quantum sensors and so on. So in the tutorial next week, I think we'll talk about this interferometry example, and you'll see it more explicitly how to derive all these things. Okay. So what's left to do for us is now see the actual interference pattern emerge for this experiment. And last year I spent like 3 lectures trying to do as exact a calculation as possible, which I mean, it was a lot of effort for very little conceptual insight. So this year we only do a very simple approximation. And I'll tell you what it will be. So in that case, we had the 2 waves going from below, and we had to wait for them to kind of spread enough that they overlap, and then you measure, right? And this was all in 2D. And now to make them overlap, we're going to be in 1D, and we'll just send them towards each other. So we'll start with a Gaussian here, moving in this direction, and a Gaussian there, moving in that direction. Okay, and we'll wait for long enough that kind of the center of this one will be here at the middle, and the center of that will be here in the middle. And then we'll see what the final wave function is, and you'll get something like the same. So this is going to be phi of t. Okay. Right, so instead of evolving them like this and having to wait for them to spread, we're going to send them like this. And in fact, we're going to send them for such a short time, so they're going to start close enough, short time that we will simplify the Hamiltonian a lot. So let me just tell you what the approximations is. So short time and large mass larger than, I don't know, t and h bar, all the quantities that we normally care about. And initial state, there's going to be these 2 Gaussians. And what this will do is that, do you remember our delta x squared? This was something like delta p squared, mu squared. There might be another factor here, t squared plus initial variance. So the idea is to make this very close to 0. And the way we'll do this is by approximating the Hamiltonian by a much simpler version. And I will do this and then I'll have for lunch so that we'll start from there. So the idea is, well, we have H is our P squared by 2 mu. And we're just going to define some P0 for like the initial state, for example, but it doesn't matter. We define a quantity P0 such that we can always write P as P minus identity times P0 plus identity times P0. Didn't do anything. This thing here I call P squared, P prime. And the idea is that we choose P0 such that this thing, when applied to the states that we care about, is going to be very small. So we choose, that's why we choose P0 to be like the initial momentum. So if you do this, then the trick is that we take our Hamiltonian. Or maybe I'll just write it like this. So then we have P squared. So I write it as identity P0 plus P prime squared. And this, I'll say, well, this is then P0 identity squared plus P0P squared, P0P prime times 2 plus P prime squared. And then if I have the Hamiltonian, then it's this whole thing divided by 2 mu. And what we do in the approximation, justified by those things we said before, that mu is very large, time is going to be very small. This thing we neglect. Okay, so we say this is approximately 0. Okay? And we get rid of it. And this again is a trick, which will turn out that the unitary is approximately true when we for very small time. So then we have this thing, and now we can expand P again. So we have P0 square identity 2 mu plus 2 P0. This was the original momentum minus identity P0. 2 mu. And this is now, so you get P times P0 over mu, which is momentum over mass. It's just what we call the velocity. So we just call this V0. Plus, minus a constant, which is going to be squared over 2 mu. And why is this useful? I'll just do it here. And I send you off. Is that then when you do the Hamiltonian, the time evolution, then U of t, which is e to minus I t. This factorizes to just having, to e to I t. That's this thing here. Yes, e to minus I t over h bar v0. Okay. Now this operator we know very well. You just looked at it in the tutorial. So this is the modular momentum. And the advantage of this that we'll see in the next lecture is that when you act with this on a state, it just shifts the position wave function, right? So then it's much easier to do all this calculation. Again, this is only approximately true for very small time. But turns out that this Hamiltonian that depends only on p and not p squared is good to describe the movement of particles that don't have a mass. For example, a photon, then they travel with p and not with p squared as a Hamiltonian. Yeah. So what we did was look at the big picture of the double slit experiment, see why it works, applications. Not to do the exact case, we'll do the exact approximate case, right? Of just 1D to see this interference pattern happen. So we'll continue this in the next lecture. And no, I almost let you out early, but we still had 2 hours to catch up, so I think it's okay. All right, so see you then next week. Thanks. I'll just turn off the thing.